Again, good morning and welcome to Astronomy 100. Today is Tuesday, September 7th, immediately after the break that we had yesterday. I hope that you guys have had a good weekend because of this extended weekend. So there was some announcements that you guys have received, and hopefully you guys have had a chance to go through it. And the announcement should have come around 7:30 in the morning today. And basically, it's about an extraordinary session I'm going to have this Thursday at 9 a.m. I did not send the link yet to it, but the link should arrive on Thursday, 8 a.m. So Thursday, you will receive at 8 o'clock in the morning, you'll receive the link. Because in the past, what happened if I send the link way too early, like today, for example, it gets buried down in the your email, and you will have difficulty finding the link. So what I normally do is I send the link immediately before the meeting, about an hour before the meeting, so that it's still there fresh in the top of your mailbox, so that you can go to it and join us. The meeting is with several sections, and the meeting is really talking about the Stellarium, the software Stellarium. Because some of you guys expressed basically anxiety and issue with the software. So I want to go through one session, basically going through everything, especially those shortcuts, because in the activity that is actually optional, because we are still trying to get used to the Stellarium. So you guys have had difficulty with those shortcuts, the keyboard shortcuts, especially if you don't have it installed on your computer and using the web version, you'll have to use the mouse. So we'll go through that activity especially, and we'll also go through the installation process for the software. So basically, that's the whole idea. Now, the thing with this meeting is not required for you guys to attend it. So if you're familiar with the Stellarium, if you have used it, you don't have any difficulty with it, went through the instructions in there and feel confident that everything is good, then you probably you don't need to attend it. But if you have difficulty with it, you're urged to attend it. If you cannot attend live because it's not normally when we meet, so what you can do also is you can watch the recording later on. There will be no prompts, there will be no assignments based on that session. So in other words, it's up to you. So I'm hoping that you guys join us on Thursday at 9 o'clock in the morning. And if not, then you watch the recording later, because probably you already have committed to other classes or you're working or something else. So Thursday at 9 o'clock in the morning. At this point, it's planned for 2 hours, but it may take a lot less than that, probably an hour or so, and we will be done with it. Unless you guys have questions, and then maybe we can explore those things and further develop stuff as we go along. So that is again for the announcement that you have received at 7:30 in the morning. Also, this week is slightly different. So let me share with you this week to show you how this is different, because normally we have about 3 to 4 units per week. This week, no, we only have 1 unit, unit 12, all of it, okay? The focus is on unit 12. So let me share with you basically what we have this week. Let me first switch to student view from your vantage point. Let me minimize. Yeah, let's keep it that I don't have to minimize that. So let me share the screen. And you should see basically Astronomy 100-10. I need at least, what is the chat thing? I need at least one person to confirm that that's what they're looking at. What you guys are looking at.
Yes.
Okay, very good. Thank you. So this is the previous week. As you can clearly see, the previous week had 4 units, okay? Plus these 2 assignments. Today, it's only 1 unit and 1 quiz. But don't be fooled with this one. I mean, the reason why it's there, it's actually for a reason. This is going to be part of, it's going to be tested in several ways. You will have a prompt today. So a discussion item. You will be quizzed on it down the road. You will have homework assignments on it, and you will also be a part of exams. So this is going to be tested thoroughly, okay? So what I'm saying in here is this is important stuff, okay? So let me stop sharing this screen and share with you another one if I can find it. Let me stop the share first and share. Where is the pop? Here, unit 12. Okay, let me pull the chat session again. You guys are looking at unit 12 learning objectives, correct?
Yes.
Correct.
Very good, thank you. So this is the stuff that is going to be covered today. The discussion is going to revolve around Kepler's laws. So that is what you're going to be doing today. Why this matters? Because we would not be here today, in my opinion, and actually you can ask any expert in the field, if we did not develop the things that happened around the 1600s. This is the 17th century stuff, okay? Things that happened then, starting actually from the 16th century, from the century before, okay, with Mr. Copernicus. We would not be here talking about what happened then. We would not probably be enjoying the technology that we have now. Somebody might argue and say, okay, if Mr. Kepler did not find these three laws, then somebody else might. It could, but it could not. Probably it could not have happened in this order. It might have happened a little later, which would probably put us way back in technology. So you'll see, and I will explain the point in here, that there is actually a sequence of events that happened, and that sequence of events that happened enabled us, first of all, to come up with, to basically anchor the scientific method in place, number one. And the scientific method is what enabled all of this technology that we have in place, number one. Number two, also, the ideas that came from here led to much more ideas down the road, led to the more inventions in science. At some point in the 19th century, 1873 to be more specific, that year, 1873, still we were in the Wild West in here, okay? A student, Max Planck, was a student of Van Pauli, and Van Pauli, who was a teacher at that time, when Max Planck asked him basically what he wants to do, I mean, what major, what field that he wants to take, he advised him against physics. Told him, whatever you do, don't do physics. Why? Because he said physics, everything that we know, remember, we are in 1873 or 1878, I don't remember, one of the 2 years. I think it's 1878 or 1873, okay? Now it sounds more, since I said it's probably more like 1878. Anyway, the point being, I told him is that everything that we know has already been discovered in physics. So there is no point in there, basically. It's a useless subject. That was before quantum mechanics was developed, before actually Mr. Planck is the one who discovered, basically laid the first stone in quantum mechanics, okay? His student himself, actually, when he majored in physics later on. And then relativity, and now we have computers, everything related to what happened in solid state physics and everything else. So the point being in here is that we always, wherever we are in time, we think that we know it all, and probably we don't know that everything that we know is there, but just around the corner, somebody else will discover something new that is going to revolutionize this thing. And revolution happened in the work of Copernicus. That was a major, major revolution. Imagine for thousands of years, we held the belief that the Earth is the center of the solar system, and for a good reason. It's not an unjustifiable reason. It's for a good reason. You and I tonight, if we go outside and look at the sky, we see things revolve around the Earth. The Earth is the center of everything. Everything seems to revolve around the Earth, including the sun, by the way. Early in the morning, it was way back in the east, and now it's somewhere in the little bit in the sky, and as if I follow it, I will see it going around the Earth day in, day out. So the sun revolves around the earth. There was no question about it. We can see it. You and I can see it tonight, today. Everything revolves around the earth. That was the geocentric model. So this belief was anchored in observation, day-to-day observation, which begs to ask the question, why Earth? Why is the Earth is the center of everything, it seems? Well, there is a good reason for it, we believe. It's because of us, humans. We are it. We are the center of everything. That's why it revolves around the Earth. That's what they believe then. I mean, who can deny it? That was actually sound arguments. It seems to be true. So, and okay, if we go outside anywhere in any direction, it doesn't matter which, you're going to find mountains, hills, valleys, rivers, and canyons everywhere. I mean, maybe a small canyon and a big canyon, but the Earth is not smooth. It's not perfect. You ask me why that is? Well, I don't know. I mean, I look at the moon and it looks perfectly shaped. And I can tell you, probably that's exactly what the belief was then, is because men sinned. Yes, we are the center of everything and everything revolves around us. Because of our sin, maybe that's why the earth is not perfect, why it's not smooth, why it's not nice. It's messed up, okay? And that is as a consequence, as a punishment for us humans, because we sinned. So that was the belief that was held for a long, long, long time. Came Mr. Copernicus. He was asked to fix the calendar, that's all, by the church. In looking at the data, looking at, among other things, the retrograde motion of Mars, looking at things, he looked at it and said, you know what? I think the Earth is not the center of everything. I think the Earth revolves around the sun as much as Mars does go around the sun. For that matter, Venus also goes around the sun, and so does Jupiter. It seems like everything revolves around the sun. It does not revolve around the Earth. Of course, that's not good. That was bad. I mean, people did not, I mean, I can go, you and I, we can go and see this on a daily basis. So why do you say that? Obviously, that made more sense to him based on the observations, based on the data that was collected for a long, long time then. So it made more sense for him that the sun is the center of the solar system. This is the so-called heliocentric model versus the geocentric model that held before him. Tycho Brahe, later on, who was a wealthy Danish astronomer at the time, he went to an island near Denmark, and he built an observatory with no telescope at that time. And he started observing the night sky, especially the planets. And he collected a huge amount of data. On this day, this planet was in this location, this planet was in this location, and this location, and the next night, and the next night. And imagine the amount of data that he has already collected. It was a lot. It was overwhelming, even for himself. Mr. Tycho Brahe, at the end, hired the young Kepler to help him with the interpretation, but he was very protective of his data because he did not want the fame to go, first of all, because of the fame, but the other thing also because he had some strong beliefs about the paths, among other things, that they have to be circular. Because here is the thing, heavens are perfect. The paths of the planets must be circular because heaven is perfect. All of the heavens, basically, the skies are perfect. The only reason, again, why things are not so perfect on Earth is because of us men. That belief even dragged later on. After Mr. Kepler abandoned the geocentric model, he came up with the heliocentric model. Mr. Kepler, after looking at the data, of course, he did not have access to all of the data until actually Tycho Brahe passed away. And the first thing he did was abandon the notion that the paths are circular. They are not circular anymore. Some of them are very, very close from circular, but not quite. They are elliptical. Elliptical paths. That's the first law of Kepler. Based on the data, based on observation, not anything else. Not based on some weird idea that circles are perfect, hence the Earth. No, based on just the data, based on observation. So it's an empirical law. It's an experimental law, the first law. The second law, if you imagine, not really, if you imagine that there is a line that connects the planet to the sun. Of course, they're still going around the sun. So if you take a line and connect it from the sun to the planet, it doesn't matter which, Earth, Mars, Venus, it doesn't matter which, okay? Jupiter, Saturn, for that matter. Take that imaginary line, not real line. There is no highway between us and the sun. There is no straight line that joins us. If you take a hypothetical line and connect it between the planet and the sun, that line sweeps equal areas at equal amounts of time. Meaning, which is critical in here, because the path is not circular. At some point, the planet is going closer to the sun, and at some point, it's further away from the sun. When it's closer from the sun, it has to move faster so that it covers a bigger arc over a shorter radius because it's closer. Whereas when it's very far, the arc it covers is smaller than the arc when it's nearby because the radius is much bigger. So the area is proportional to the square of a radius, and also the angle. So the angle must be less. So that was the second law of Kepler. The third law of Kepler took him a little bit of time to come up with it. And the third law of Kepler basically states that now we know the Earth goes around the sun once a year. That is basically what we call a year. If you are 24 years old, that means the sun or the Earth went 24 times around the sun ever since you were born. That's exactly what the year is. Now, the distance from the Earth to the sun is what is called actually the semi-major axis. Okay, we're going to get into the properties of the ellipse. If you square the period, you square the year, and you cube, that means you multiply the semi-major axis 3 times by itself. Semi-major axis times semi-major axis times semi-major axis. That's what the cube means. The two numbers are the same. This took him a little bit of time to invent it, and because of the fact that required a little bit more math. So these are the 3 laws of Kepler that he came up with. Obviously, this is based on data. Data don't lie. Numbers don't lie. Based on the work of Tycho Brahe. You see how important this stuff is? If it were not for Tycho Brahe's data, Mr. Kepler would not have access to that much of data to come up with these 3 laws. They're solidly anchored in numbers. It's not like something that is based on, that is somehow a loose theory or something like that, okay? So that is the state of affairs at that point. Mr. Galileo took a toy, which was the telescope, which is made of 2 lenses, basically. You have a lens that has a certain focal length. The rays come from the faraway object parallel to it, but they are focused on a single point. So basically, you can see with a little bit more detail an object that is far away from you. That's what the telescope is. At some point, we're going to be talking about telescopes. Now, he turned that toy, after he modified that a little, toward Jupiter. And here is, before his eyes, he saw the first night 3 objects, 3 moons actually, revolving around Jupiter. The second night, he saw the 4th one. Now we know what they are. Io, Europa, Ganymede, and Callisto. Those are the 4 moons of Jupiter, the big moons. Jupiter has 72 moons or so, okay? But the big ones are Io, Europa, Ganymede, and Callisto. Now we call them actually the Galilean system or the Galilean moons, okay? It's the same thing. So basically, the point in here is these 4 moons, they don't revolve around the Earth. They revolve around Jupiter. So the idea that the Earth is the center of everything, and we are it, and everything revolves around us, and we are the point of the whole universe, and everything is not true anymore. Because here are 4 moons that don't revolve around the Earth, but rather revolve around Jupiter. That's one thing. So that was a major contribution of Galileo. Here, take a telescope, look at it. You don't have to believe me, just look at it. So the heliocentric model now is more anchored as far as the planets, and the geocentric model is basically completely dead. No more, okay? With just this observation. The second observation of Mr. Galileo was, with the same toy, he looked at the moon, and he clearly saw that those dark areas of the moon are shadows of hills on the moon. They are projection from the sun on the moon, so indicating that the moon has hills and valleys. So the idea that the heavens are perfect and the circle is perfect and the planets have to go in circles because the heavens are perfect, and the only reason we have mountains and hills in Earth is because men sin, is not true anymore, because here is another object in the sky that we can look at, and here it is, look at it with your own eyes. It has also hills and valleys. Who sinned there now? So you see how things are interconnected now. A lot of those basically things that we held for thousands of years, they fell apart with the work of Copernicus first, Tycho Brahe second, Kepler, and the observations of Galileo. Powerful stuff, okay? Extremely important things. Obviously, this things is based on observation of what we see day in, day out. I'm going to talk a little bit of why I think what happened in the 1600s to 17th century is really what led us to today. Okay, I'm going to mention that. Before I do that, since the second item is the properties of the ellipse, which is how the planets go around the sun. I drew an ellipse in here. Let me stop sharing the screen so that you can see it in the big screen, okay? I drew an ellipse in here. So this is what an ellipse is. So what are the ellipse? The ellipse has characterized by these 2 main things, which are called the focal points, okay? These are the focal points of the ellipse. In the case of the circle, the 2 focal points fall apart on one another, and they become the center of the circle. So the circle is actually a special ellipse where the 2 focal points are the same. So the ellipse is more general than the circle, number 1. Number 2, this is the sun. The sun sits in one of the focal points. Which one the sun sits on, it doesn't matter. Just one of the 2. They're both symmetrical. So the sun sits on one of the focal points. And the planets go around the sun in this path, elliptical path. So that was his first observation. That was his first law. So today's discussion items is to list the 3 laws of Kepler. Put them in your own words, or copy them from the book, or get them from Wikipedia. I don't care. The point is you have to know the 3 laws of Kepler. So the first law, the sun, which I try to have it in yellow in here, sits on one of the focal points of the ellipse, and the planets go in orbits. So what is again the ellipse? The ellipse is characterized by this distance from this edge to this edge on the part that is kind of extended. This is called the major axis. Half of it, just right in the center of symmetry. This is not the center of a circle, okay? It has nothing. It's just the center of symmetry. Half the distance between the 2 points, which are called perihelion when you are close from the sun, and aphelion when you are far away from the sun, okay? So the nearest point is the aphelion, the furthest point, this is June 21st, and this is December 21st, okay? So when you are in these 2 points, the distance between the Earth and the Earth, basically in the 2 positions, is called the major axis. Half of that is the semi-major axis. Half of this distance is the semi-major axis. Now, from the flat side, which is from the bottom to the top, that is actually the minor axis of the ellipse. Half of that is the semi-minor axis. Half of this distance is the semi-minor axis. In algebra, the small distance in here, they call it B, and this distance, they call it A. Okay, so you see symbol A used. That means it's the semi-major axis. Twice A is the major axis. Little b is the semi-major axis. Twice b is the whole thing. Okay, the distance between the two focal points usually, or twice of it, is called 2c. So the letters are A, B, C. Okay, and half of that is c, just to stay symmetrical. That's all. How far the focal points are from each other represents the bulge in the axis. If there is no distance at all, or if they fall on top of one another, we're back to a circle. And these two distances will be the same. So in other words, there is no bulge. The whole thing looks circular, symmetrical. If the distance is extended, like in this example, this is highly eccentric. Okay. For the case of the planets, most of them, the two focal points are actually inside the sun, which means that their paths are very close from circles, but not quite. Okay. I did not get into it, Carlos, yes, but I'm going to. So I'm going to tell you exactly what it is, but I'm just trying to build up the concept in here. Okay. So for the case of the planets, the distance between the focal points is very close from one another, not exactly the same, but close, and it's inside the sun. Hence the eccentricity, which is another property of the ellipse. The property of the eccentricity is basically how far these 2 points are from one another. So the eccentricity in this case for the ellipses is very close from zero, not zero. Zero is for the circle, because this distance will be the same. I mean, there will be no distance, but usually there is one. This is exaggerated, by the way. This graph in here is exaggerated because for the case, most of the planets, the 2 points are inside the sun. Okay. So in this case, the eccentricity is not zero, slightly more than zero. Some planets, though, especially Pluto, for example, or Eris, which are which we call them dwarf planets, they have high eccentricity. Mars also has a little bit of eccentricity. All of the other planets, they have very low eccentricity, including Earth, almost zero, but not quite, which means that they are not exactly circular paths, but they are still elliptical paths with low eccentricity. So again, the properties of the ellipse are the focal points, the semi-major axis, the semi-minor axis, and the eccentricity. So these are some of the concepts that we're going to explore. Now, the first law, again, is that the planets go in elliptical paths, where the sun sits in one of the focal points. That's basically the first law. The second law, if you imagine a line, let's say the planet is here. If you imagine a line that joins the planet to the sun, that line sweeps equal areas at equal amounts of time. Let's say, for example, in 1 week near the perihelion, it goes this much arc distance. When it's far away, it needs to spend a little bit of arc distance, so that this area extended is the same as this area in here. Okay, meaning that when it's close from the sun, it has to go fast compared to when it's far away. So it's like this. Okay, so you have this motion near the sun, which is fast, and then it slows down, fast, so it slows down. Okay, so that is basically the second law. The second law, a line joining the planet to the sun sweeps equal areas in equal amounts of time. The third law of Kepler is a little bit more work in here. Let's say, for example, today is what? September 7th. If I wait September 7th, let's say, for example, the Earth is somewhere in here. Okay. If I wait a whole year, the Earth will go around and come back September 7th, 2022. The Earth would have exactly 1 year. September 7th, 2020 was also here, where the Earth was here too. So that's a period. So the period is the time it takes to go once around the sun. And the semi-major axis is this number, or this number, it's the same thing, okay? If you cube this number, A, you cube it. Do I have it backwards? I'm sorry, okay. If you cube it, this number, if you cube it, or this number, if you cube it, it's the same as this squared, provided the period is expressed in years and the distance is measured in astronomical units. So these are the 3 laws of Kepler. Again, now to answer your question, Carlos, and we're not done with the prompt yet, because we're going to talk about it a little bit more and more. This is today's prompt, is to list the 3 laws of Kepler. Make sense?
Yeah, it does.
Okay, very good. So again, are you looking still at the learning objectives? I just want to make confirmation here.
Yes.
Okay, very good. So again, these are some of the properties of the ellipses. Again, if you go and get an ice cream cone, okay, you will see that the cone has this shape, basically, all the way around. It has a base area, and the top is really a pointy thing. And between it, it's slanted, okay? If you take the cone and cut it right in the middle, parallel to the base, you're going to produce a circle. Okay, so a circle is a shape that you can make out of the cone. Clear, no problem. Now, if you cut it not parallel in the base, but it's slanted. So in this case, you're going to produce an ellipse. I'm sorry, slanted. Okay, or slanted like this. So you're going to produce an ellipse. So it'll have 2 focal points. So also the ellipse is a shape that you can cut out of a cone. Now, if you cut it right in the edge and you bring it to the base at a different angle, and in this case, you're going to end up with a parabola. So a parabola is actually another cut from the cone. If you cut it right outside, now actually you're going to end up with a whole hyperbola, which is also a cone from the shapes. So all of these 4 shapes, they're actually conic shapes. So the circle is just a special cone, a special cut from the cone that is parallel to the base. A more general one is an ellipse. So the ellipse and the circle, they are cuts actually that cover from end to end, from one side to the other side of the cone. Now, the other 2 cuts need to be happening in special points, but they also can be cut from the cone. So they're called the conic shapes. It happens, according to the first law of Kepler, that the planets we see are part of the conic shape ellipse, with 2 focal points and so on and so forth. Why am I saying this? Because it's important for what's going to come next. It's very important to understand that all of these shapes, they're actually from the same initial shape, which is a cone. Okay, you'll understand the connection of all of these 4 shapes. Okay. We use still circular paths, for example, for some of our satellites, and we have conditions for them so that we can have them for GPS. So all of these things exist, actually. All of the shapes exist, all of the 4 of them. But for the case of the planets, it's only the ellipse, okay? At least the known planets then. Okay, list the 3 laws of Kepler and carry out calculations using them. So we're going to do that today. We're going to do calculations today based on the 3 laws, okay? Obviously, the first law, you cannot calculate anything other than just describe things, okay? So is the areas also, you cannot really do a lot of calculations, at least at this level, okay? But the main calculation is going to be with p squared equals to a cubed law, the 3rd one. So we're going to do that today. And then discuss the Galileos, and I already mentioned that. Let me put things in perspective so that we know what's happened and why I think this is probably the most important development in science that happened basically throughout, including today, okay? It was a major, basically revolution in science. Because around 1650s, 1654, or just before that. Just like we are right now, London and England was hit with a pandemic, similar to where we are right now, with the plague then. Okay? So people were asked to do social distancing. Everybody go home, basically, from the universities and colleges. Don't stay here because it's contagious and everybody could die. So the campus is closed and students were sent home, just like what happened. The only problem then is they did not have Zoom, that's all. Okay, so they could not do their classes online. So basically everybody was on his or her own, including one student in particular, and that was Mr. Newton. Mr. Newton was still a student and he already came up with 3 laws of motion. The law basically of an object under no acceleration, an object under accelerated motion due to forces, and an object in interaction of objects. So yeah, at that point, he was a student. He already came up with 3 laws. Excuse me. Mr. Kepler's work was way back in the early 1600s. So as he was sent, like everybody else, to home, he was handed the 3 laws of Kepler. Here are the 3 laws of Kepler. Look at them. Planets go in elliptical paths, planets sweep equal areas in equal amounts of times, and also planets require that their period squared is equal to their cube, semi-major axis cubed. And that is true for all of the planets that we knew then. Can you explain them based on your laws? Mr. Newton, first of all, had to discover the law of universal gravity, the law of gravity, number 1. Number 2, he was able to explain the laws of Kepler. Number 3, he was able to predict, I mean, based on his work, you can predict things that will happen in the future based on those laws. One of them is Halley's Comet. The other one is actually Neptune and Uranus. Uranus was discovered by accident, but Neptune was discovered because of these laws. 2 mathematicians independently, one in France and one in England, they calculated and saw the wobble in the motion of Uranus, and actually more so the Saturn, actually, around the Jupiter, and actually away from Jupiter, can only be explained by the existence of another planet, which is Neptune. At that time, they didn't know it existed. Based on their calculations, they said it must be in this point in the sky. So turn your telescopes and you will find it. And sure enough, the German society, they turned their telescopes and they found Neptune. Later on, even the British society, they turned their telescope and found Neptune. So that's how Neptune was discovered, based on these laws. But more so on the work that followed later on of Mr. Newton. So Mr. Newton's explanation actually went way beyond that, because his law is supposed to be universal, takes the laws of Kepler and applies them for everything else that we know, including galaxies and everything else. So it's amazing stuff. You go from this solar system down to other solar systems and other planets. The only nagging issue then, and I'm going to come back to it, was Mercury. Okay, so before I come to Mercury, let me explain exactly what Mr. Newton did. I mean, how he came up with the solution. First of all, his solution for the paths was not just elliptical. Ellipse was just an exception. As I said before, the circle is an exception of the solar ellipse, so that was already included in the work of Kepler. He found that among other solutions is actually the parabolic solution and the hyperbolic solution. The only reason why we don't see planets of those types is because they must have been ejected a long time ago. And objects in the solar system, not just planets, by the way, including asteroids and even comets, they obey the same laws. So those things, if they existed, and they must have been ejected from the solar system, because again, when you follow parabola, it never come back, and hyperbola, it never come back. So those are ejected. So the only reason why we deal with elliptical paths is because those are the things that have that are basically attracted strongly to the sun, and we see them. They are certain. So that is one thing. So the path is solved with Newton's solution for the universal law of gravity. The second thing is why the planets sweep equal areas with equal paths, and that is because of the conservation of angular momentum. Because there are no external torques. So the angular momentum must be conserved quantity. And in doing so, it explains two things in the same time. First of all, why all the planets are on the same ecliptic. If you find a planet that is above or below or slightly off, it's because something must have happened to it. But for the most part, all of them are in the same ecliptic, the same plane. And that is because the angular momentum is a vector, and that is a direction of the angular momentum. So the direction must be conserved, so everybody has to be on the same plane. That was one thing. The second thing also is the magnitude of the angular momentum is conserved, and the magnitude of the angular momentum is actually the area, okay, that is swept by those imaginary lines. So the conservation of angular momentum is coming as a direct consequence of the work of Mr. Newton, or at least it can be explained by the work of Mr. Newton. So that's the second law. So we nailed both the first law and the second law. The third law, actually, you can do a little bit of work on the energy, and you will find the third law becomes a consequence of that, namely the square of the period is proportional to the cube of the semi-major axis. So that was also a consequence of the work. So again, as I said, if a theory, and here is the point I'm trying to get into, in terms of why I think this is extremely important, because it laid the foundation of the scientific method far more strongly than anything else at that point. If a theory, all it does is explain what somebody has seen or observed, it's not good enough. If all Mr. Newton did was explain what Mr. Kepler did, that is useless. I could come up with all kinds of explanations for you guys, okay? But it doesn't make sense. The only thing that is going to be useful is if you can do something more with the theory. First of all, he was able to find where that constant means. Why the square of the period is equal to the cube of the semi-major axis, and the ratio. The ratio has to do with the mass of the sun. Because when Mr. Galileo looked at the Galilean systems, Io and Ganymede and Callisto and Europa, when they revolve around the sun, the Jupiter, the constant is different. It's not the same constant as, for example, Jupiter revolves around the sun, because the mass of Jupiter that holds them together is different than the mass of the sun. So that constant now has an explanation. We didn't know about it when Mr. Kepler was doing it. He just looked at it blindly. It's just a fixed number. It doesn't change. That fixed number has to do with the mass of the sun. That fixed number is different if you are, for example, the case of the Earth and the Moon, because the Earth's mass is different. That case is different, for example, with Mars and its two moons. So it depends on the object. And now we can use that work and explain how the mass of the black hole in the supercenter of the supermassive black hole in the center of the galaxy, just by observing how fast the stars go around it. So we can find its mass now. So the work of Newton went a step beyond. It gave us some other things we didn't know from before. That's why it's good. That's why it's strong. It also was able to predict when Halley's comet is going to come. So when Mr. Halley looked at that comet and he looked at it over a certain period of time, he predicted its path, and he said that in 76 years, a day from today, in 76 years, you're going to see this comet come back again. And sure enough, within a few days, it was back in the same time. Within a day or two, actually, it was visible in the sky. That is powerful stuff. So if a theory can only explain what has been observed, it's useless unless it does something beyond, and this did. It predicted for us the existence of Neptune, and sure enough, we found it. It's a big planet, Neptune is, and also Halley's Comet and other massive objects and how things revolve around them, and everything else. The problem was Mercury. So imagine what happened then after that. Now we have a very solid knowledge about everything that we know based on that point, and things are looking great at that point. And things start to develop, mechanics and then thermodynamics, and a lot of things happen because of the scientific method and what revolved around all of this time and the time. The problem again was Mercury. Mercury's path was wobbling a little bit, which was an issue. Everybody was going around the sun in the plane, the ecliptic plane. Mercury was going like this. So it was an issue big time. And then in addition to that, it was not, the period was not exactly correct in a sense like everybody else. So no matter how much you try to fix the calculations and the observations and maybe include the effects of Venus, maybe include the effects of Earth, maybe include the effects of Jupiter, it was not good enough. It was hard. That's why, you see how people were working day in, day out, trying to explain things based on what is known. And then when everything else fails, they have to come up with something new. And that is the work of Mr. Einstein, actually. That happened in the 20th century, about 100 years ago. That was, of course, led to the relativity, which led to other branches of science, which led to other work and everything else. And now here where we are. That's why I believe what happened in the 1600s was of a great importance for us to what happened now, because it led to a sequence of events that led us to where we are today. Okay. So this unit, and it's a unit by itself, it's extremely important for you guys, as I said. It will have a discussion item today, and that is list the 3 laws of Kepler. I'm going to write them down myself, and you can interpret them in your own words or even copy them from somewhere else. It's not as long as you have them. Okay. That's a discussion item for today. You will be quizzed on this one. You will have homework assignments on this one, and you will be tested on this one.
Okay,
So
Mr. Lucidi.
Okay, thank you. Okay, so it's going to be important stuff. So let me share with you another screen in here, another thing in here. Let me find it first. Why is this thing closed? This screen, but let me close this window here. Probably it's going to help a little bit and keep that. I need it. Let me open this and let me share my notes. For that, I need you guys to open. Let me get the chat session also going, just in case. I'm gonna go to page. I mean, you really don't need the book, but I'm hoping that at some you will need the book for this parts of Kepler. Excuse me, I need to drink something. Okay, so you will need page 95. From either book, it's page 95, I believe. From either edition, it's 95, okay? Yes. It's page 95, and for that, you have a table in there. I'm gonna pick up Mercury for sure, as an example of calculations. I'm gonna pick up another planet, probably Saturn, okay, and see how things look like. Okay? So, if you look at the table, which is 12.1, it gives you Mercury and how far Mercury is, or at least what is its semi-major axis, namely A. A is the semi-major axis for the ellipse, which is A. A for Mercury, according to this table, 0.387 AU. And then it tells me also the period P, 0.241 years, meaning it's almost a quarter year for us, slightly less than a quarter, slightly less than 3 months. Mercury goes once around the sun. In 1 year, Mercury takes what is it? In 1 year, Mercury takes 4 years. So from September 7th, 2021 to September 7th, 2022, Mercury would have gone 4 years around the sun. 4 of its own years is 1 of our own year. That's what this numbers mean, okay? And its path is slightly less than 0.4, that of 150 million. So if you really want to know how far it is from the sun, just multiply this number by 150 million and you will know it in kilometers. But we don't care about that. We'll leave it in astronomical units, namely compared to the Earth. That's what astronomical units mean. So what we do in this case is we take A cubed, which is really 0.387 times 0.387 times 0.387. So that is basically what this cube means, okay? And multiply it with the calculator, with the note, and it's extremely important to know the following, that you are dealing with 3 sig figs. 1, 2, 3. So when you're given a number in 3 sig figs, the maximum you're going to retain is just 3. You cannot retain more than that. If I plug them in the calculator will give me more numbers, but the calculator doesn't know, you know. So when you do stuff and you compare things, you have to really be mindful of this fact. So let me pick up the calculator and let me move it to the other side for it now. Or at least keep it in here, that's fine. Okay, because I don't want to lose the chat on that side, because I want to have the 2 screens going on at the same time. So let me stop sharing. Okay, let me stop sharing the notes and let me share with you the calculator just to show you what the calculator will do for me, okay? So if I plug in these numbers, this is what the calculator is telling me. 0.387, this calculator, if you do multiply, you have to do a star, times 0.3, not 0.3, 0.387 times 0.387, okay? So I cubed it, okay? I could have done 0.387 to the power 3, but I just cubed the thing. So it's telling me, according to this calculator, 0.057960603. That is exaggeration. That is not correct. Why? Because of the fact, this is what the calculator says, but I don't accept these numbers. I only am allowed to retain 3 significant figures. Here is what I know how we do significant figures. Anything past the 4th significant figure, I'm going to ignore. So in other words, 0 and a 6 and a 0 and a 3, I'm going not to even talk about it. I'm going to ignore them. The 4th sig fig will determine what comes next. The 4th number will determine what comes next. And the 4th number is more than 5, it's 6. As long as it's more than 5 or 5, I'm going to round it up. If it's less than 5, I'm going to drop it as well with the others and ignore it. At this point, it's clearly 5 or more. It's actually 6. So I'm going to round it up and make it a 10. Make it actually in the next number in the digits. Now I have a 1. 1 plus 9, that's going to be 10. So I'm going to have a 0 as part of my answer. And then part of the 1 from the 10, I'm going to add it to a 7, it becomes 8. So it's going to be the correct answer is 0.0580. So that is so that you know how to do that. Okay, if you have a calculator that does rounding, and there are a lot of them out there, this could be easy done by asking the calculator to retain only 3 sig figs, and it will do the same thing. Excel does that too, if you are really familiar with that. So let me share with you the screen. And let me go back and tell what the answer. So a cubed, according to my calculator, is equal to 0.0580. Again, it was a 9 in here, but I rounded up the number before it. So the 9 goes up to 10, basically. And then it was a 7 in here, so it has to go up because this one went to 10. So this has to go up to 8. And this does not change because I did not carry 1 from this operation. So this stays the same. So this is what a cubed is, okay? Let me do p squared. Let me take this number and square it. So p squared means equal to 0.241 times 0.241. This too has 3 sig figs. And even if it had more 3 sig figs, I can only retain 3 sig figs because the first one had 3 sig figs. And the 3 sig figs in this case are the 5, the 8, and the 0. Those are the significant figures. That's what sig fig stands for. So those are the main numbers. These two before the decimal points are irrelevant, okay? But I have to write them because that's a number, 0.0580. So I cannot say it's more than that or less than that. Okay, so I have to go back into the calculator and plug in that number and do the same trick. So I'm going to go share calculator. I'm going to do 0.241 times 0.241. According to this calculator, it's 0.058081. Again, I'm going to ignore, because I have three sig figs, 580. I have to ignore anything past the fourth digit. And the fourth digit is an 8. So anything after that, like the 1 in here, I don't even talk about. The 8 now, I ask the question, is it 5 or more than 5? Obviously, it's more than 5. So it is, yes, it is 5 or more than 5. So I'm going to promote it upward. So the 8 becomes a 1, actually, because it becomes a 10. 10 plus 0 is 10. So this becomes an 8. This stays the same now. They don't change because they don't carry anything over. So the correct answer in here is that p squared is, according to the calculator, my p squared is 0.0581. Obviously, I need to compare this number and this number. This is the square of the period. This is the cube of the semi-major axis. And the two numbers are awfully similar. They're very close from one another. So I can say that the third law of Kepler still holds true. Okay. I said I need to take another planet to compare with it. And I thought we should take Saturn. Saturn, anything you take from the table is going to work. So Saturn, the semi-major axis A is 9.54 AU. That means it's almost 9.5 times, or slightly more than 9.5 times as much as from the sun, as much as the Earth is from the sun. That's what this says. Okay. The period, meaning how long does it take to go once around the sun? The period P is 29.46 years. Meaning, once it goes once around the sun, in almost 30 years, slightly over 29 years. So if you happen to be 24 years old now, you are less than a year on Saturn old. You're still a baby as far as Saturn is concerned. Newborn, less than 30 years, 29 years. So it's less than a year. So this is the period, meaning how many years on Saturn. That's because it's far away. The object that is closer, this relationship requires if A is small, P is small. So it's less time. That's why for the case of Saturn, the A was very small and the year was three months, basically. It takes 3 months for Mercury to go once around the sun, whereas it takes a whole year for the Earth to go around the sun, because the Earth is far away from the sun than Mercury is. First, the same thing. It takes far more, almost more than 29 years for Saturn to go once around the sun, because it's further away. It's almost 9.5 times further from the sun than the Earth is. So that's what these things are saying, basically. But let's do the thing. Let's do the same thing. So I'm going to take A cubed for Saturn. And A cubed for Saturn is 9.5 or 9.54 times 9.54 times 9.54. Okay, I have 3 sig figs also. I have 3 numbers of significance. That's what 3 sig figs means. So the answer I'm going to retain also needs to retain only 3 numbers. I cannot retain more than 3 numbers. So again, I'm going to go back into the calculator. Share the calculator. Let's see what the calculator says. 9.54 times 9.54 times 9.54. Okay, so that's what the cube means. It's 868.250644. It doesn't matter. All of these numbers, the 5, the 0, the 6, and the 6, and the 4, ignore them. The only number to focus on is this 2. And ask yourself, is this 2 5 or more than 5? And the answer is no. It's actually a 2, less than 5. So I'm going to ignore it as well. I don't round it up. I round it down. I round it back to 0. So if this number is, that's the number that I have to focus on. The first 3, they stay. It's this one. Why is this thing not rounding? For some reason, my, I'm good. Okay, so the first 3, they stay for sure. I mean, not exactly, they may change, but I'm going to retain them. Somehow, I'm going to either add 1 to them or keep them as they are. It's this number that determines what happened to them. And this number, of course, I have to compare it to 5. The others after that, I'm going to ignore, forget about them. It's this number that is going to dictate what happened next. And ask myself, is this number 5 or more? Obviously, this is a 2. Since it's a 2, it's less than 5. I'm going to scratch it out too. I'm going to make it 0, as a matter of fact. And nothing happens to the first 3. They stay the same. So the answer is 868. Let me share the screen. So a cubed is 868. The calculator gives you more number than what you really need. That's the whole point. Because you started with only 3 numbers that you know for sure, you cannot invent a 4th one. So you can only have 3 here. And the calculator will give you a 4th, probably a 5th, probably a 6th, probably a 7th, probably 8th, so on and so forth. More than what you need, okay? And that is basically where you have to make a decision on what is to retain, okay? If you had this in algebra, you're in good shape. If you didn't have it, don't worry about it too much either. So just basically look at the end and answer and compare them. So I'm going to take the period and square it now. So the period squared. Remember, the period is 29.46. Oh, I have a problem now, because I actually have 4 sig figs. I have 1, 2, 3, 4. I have the 2, which is significant. I have the 9, which is significant. I have the 4, which is significant. And I have the 6, which is significant. So when I square it, I have to do the same thing, but retain now 4 sig figs. But at the end of the day, it doesn't matter, because I only have 3 sig figs in here. So I can only compare what I have with what I can have from here, which is, since I have more information that I need, then I have to take just the information I need, which is 3 at the end of the day. Had this been only 2 sig figs, had they given us only 29, then I have to drop the 8 in here and ask myself, is the 8 more than 5 or less? And if it is, then the answer will be 870, because I have to promote the 6 up, and that's it. But at this point, we have 4, so in good shape. Since it's 4, I'm going to, at the end, even retain 3, although I have 4. So let me go back to the calculator and tell you what I'm talking about now. Share the calculator, share. So I have 29.46, is it 46 or 64? 46 times 29.46. That's what the square means. It's telling me it's 867.8916. I have 4 sig figs. That because I have 29.64. That's what I started from, 4. So technically the answer is I have to ignore anything after the 4th, I mean after the 5th, because the 4th, the 5th is of interest to us. I have to ask a question about it. It's the 6th and the 7th that I have to ignore. In other words, the 16th, forget about them. And ask yourself, is the 9 more than or equal to 5? Obviously, the 9 is more. Then in this case, I have to round up, meaning make the 8 and 9, and that's it. So the correct answer is 867.9. So that's how the rounding works in this case. So according to my calculator, let me go back into the screen in here. So p squared then is 867.9. But since I'm comparing this number to that number, and this has 3 sig figs, this one also must also be retaining 3. So this one is actually closer to the 9 now. I ask, is it more than 5 or equal 5 or more? It is. So I have to promote it up and make it into a 10 by carrying the 1 in here. So the correct answer is 868. This and this are the same. So for the planet Saturn also, p squared is the same as a cubed. Okay. See, this is the third law of Kepler. This is what we're talking about. Provided this is in years and this is in AU. If you use different units, you're going to find them proportional and you will find a number, and that number has to do with the mass of the sun. Okay, so let me put the laws of Kepler according to my own words. You can put them in this way if you like, or you can put them on a different words. It's up to you. Okay, but the point is, this is the discussion of the item today. Okay, so Kepler's laws, or the laws of Kepler. So the first law says the planets orbit the sun in elliptical paths where the sun sits in one of the focal points of the ellipse. So that's basically what the law is. Planets orbit the sun in elliptical paths where the sun is located in one of its focal points. Which focal points? Doesn't matter. It has 2. The ellipse has 2. Okay, so the sun is in one of those 2 points. Okay, they're symmetrical. Doesn't matter which one you have. All the planets do. All the planets do. Item 2, or law number 2. An imaginary, and I want to write the word imaginary in here because I don't want you to think that there is a real line, okay? Imaginary line joining the planet to the sun sweeps equal areas in equal amounts of time. So this is law number 2. This law has to do with the conservation of angular momentum when you do the math for it, really. Okay. Law number 3. The square of the period of a planet in years, so it has to be in years, is equal to the cube of the semi-major axis in astronomical units, in AUs. Okay, so those are the 3 laws of Kepler. Those are the items of the discussion today. Okay, you can copy them from the book, you can copy them from somewhere else. As long as you post them in your discussion items today, that would be fine. Okay. Again, some of you joined us late. There was an announcement this morning that you should have received at 7:30 in the morning. And that announcement concerning a meeting that we're going to have on the Stellarium this coming Thursday. And the link is going to be on Zoom. The link, you're going to receive it on actually Thursday morning, 8 o'clock. you will receive the link for the Zoom session. You are not required to attend it. This is optional for those especially who have difficulty with the stellarium, so that we go through the stellarium training and go through the activity that was optional from week 2. And it's going to be recorded. So even if you cannot make it on Thursday at 9 o'clock in the morning, you are going to watch the recording later on if you choose to, because it's going to be posted on Canvas. And I urge you, if you have difficulty with it, either attend it live or watch the recording later. There will be no assignment based on that. Okay, so it's really because there will be down the road projects based on Stellarium. So we really want you to be familiar with it. The reason why it's important is because some of you had difficulty installing it on your machines, especially those who have Chromebooks. I didn't know, and I probably have to research this one further. You found yourself using the web version, and the web version with the shortcuts on the keyboard don't work. So you have to use the mouse. Okay. So we will go through that to have the alternatives for the mouse versus the shortcuts, so that you're familiar with it. Okay. So hopefully to see you this Thursday at 9 o'clock, if not, watch the recording. And that's all I have.
Okay, I see you on Thursday then.
Okay, thank you very much, Ivan. Okay, I'm going to stop the recording.